Okay, arrived here at the last page of the practice test. So maybe just a little, let me speak just a little generally. Chapter 10, we've got intermolecular interactions that will certainly generate some questions on the test, relating structure to physical properties, that sort of thing. There wasn't a question on here about something like vapor pressure on its own, but certainly something like that could pop up here. Most of those relate to something like unit conversion types of problems or ideal gas problem. The heat amount of energy associated with a phase change, that is fair game from chapter 10 as well. That to a large extent is a review of material from chapter 4, right? But intermolecular interactions do affect the magnitude of those values, heat of fusion, heat of vaporization, that sort of thing. So that seems like a reasonable type of thing to be ready for on the test as well. We'll see some of those additional problems on the reviews. Chapter 11 is different ways to calculate concentration and then colligative properties. That works as well. Now, I usually cover Henry's Law with chapter 11, although it actually appears in chapter 10 in the textbook. And I like it with chapter 11 because it's essentially the same type of equation. You've got a constant that relates to things. Henry's Law, it's solubility to pressure, whereas with your colligative properties, it's change in temperature, the boiling point to concentration, molality, or something like that. So be ready for those. And then, of course, chapter 12 is solids. And what I want to see you be able to do in terms of solid structure is evaluate unit cells. I'm not going to have you calculate the density based on the geometry, like we'll do in some of the practice materials that we'll do. But, I think that's a little more involved than what I want to see on the test. So a couple good examples here of what we might see from chapter 12 on the test were the last page, where we're actually just thinking about the different possible arrangements. But here, where I actually give you a picture of a unit cell and I want you to evaluate it. So let's look at these quick here. Number 6 here, what is the chemical formula of the following compound? So the chemical formula is going to relate to the ratio we see in the unit cell. And then the second thing there, what would be possible identities of the anion and cation? That will be an interesting thing to look at after we've analyzed this here. Now, the atoms we see on the edges here are a little bigger than the atoms we see in the middle. That's a reasonable assumption in most cases that the anion is the larger and that the cation is the smaller. We talked about the relative size of neutral atoms versus cations and anions back in chapter 7. Right? You add an extra electron, that causes the electron cloud to get larger, and anions are always bigger than neutral atoms. Same is true. Same idea is true when you remove an electron. You take an electron away from an electron cloud, the positive charge of the nucleus can pull those remaining electrons in more closely because we've minimized electron-electron repulsion, so the cation is smaller. So make that distinction. Certainly there are cases where you have giant cation with, you put it with a tiny anion where this might be reversed, but that, I wouldn't be trying to trick you with something like that. Looking at the anions here, the anions are on the corners of the cube and then on the faces. So we've got corners and faces. Corners, there's 8 corners. Each corner, only 1/8 of that atom is actually in the unit cell we're looking at. That will add 1 anion from the corners. 6 faces, each of those half is in the unit cell we're looking at. 3 atoms from the faces. So we have 4 anions here in this particular structure. Now if you look at the cations are all completely inside the unit cell, right? They aren't out on the face, right? In fact, that's kind of why the grid lines are here, so we can see more where the faces of the cube are, and we can see that those cations are actually inside of the unit cell. So for the cations, there's 8 of them, right? They're all in the body, right? They're not right in the center. but they're all inside the unit cell. So that's 8 times 1, 8 cations in there. Now, so our molecular formula here is 8 cations, or not our molecular formula. Within the unit cell is 8 cations to 4 anions. That would correspond to an ionic formula of 2 cations to each anion, right? Because the ionic formula will be the simplest whole number ratio of the pieces involved in the formula. Now, in order to have 2 cations and 1 anion, we would have to have appropriate charges. So the easiest way to think about this is if my cation has a +1 charge, my anion would have to have a -2 charge to match this ratio. So any formula that would satisfy those charge requirements would work for this structure. So a +1 cation could be lithium, right? And a -2 anion could be something like oxygen. So lithium oxide, Li2O, would work. Sodium is also a +1 ion, so sodium oxide. Right? Other -2s would be sulfur. It would make sulfide, so potassium sulfide would work here. Right? Selenide, telluride would work as well. So beneath potassium is rubidium, so rubidium. Selenide would be a possibility here, right? So this I like this problem because you got to think about some of the things we talked about back in chapter 2 as far as ionic formulas, which atoms have which charges, and how do those charges relate within the structure as well, right? It's kind of a nice thing to review or freshen your understanding of. Okay, similar idea here in the next structure. We want to figure out what is the charge on copper in the compound whose unit cell is shown below. So again, oxygen's your anion here. It's a little bigger than the copper, right? Even though copper, right, there's a lot more electrons in copper, there's a lot more protons there as well that kind of pull the charge in before a cation relative to an anion. So if we look at the oxygens, they're on the corners. So we've got corners, right? And we've also got an oxygen right in the middle, which is in the body. So corners, again, is 8 times 1/8. That represents 1 oxygen in the unit cell. The body, though, that's completely in there. So there are 2 oxygens in this unit cell. Now, if we look at the coppers are all completely inside the unit cell. And there's 4 of them. So these are all inside, all in the body, 4 times 1, 4 coppers. Now, actually, there's a similarity between the structure I had up here for number 6 and this one in number 7. These are actually tetrahedral holes where the cations are living. So on the previous question, we saw the cubic hole and the octahedral hole with the 2 ionic structures there in problem number 5. And right here in problem 6 and 7, we're seeing cations in tetrahedral holes. It's a little harder to see the other atoms of a tetrahedral hole because they're usually one of them is in one of the next unit cells. And anyway, a tetrahedral is weird angle compared to an octahedral, so it's a little harder to see that. But in this case, we've got 4 coppers and 2 oxygens in the unit cell. Now, that's not the right way to write an ionic formula. That's not the simplest whole number ratio of the pieces. So the ionic formula, if I could spell it, we would want to reduce those coefficients. So the ionic formula would be 2 coppers, 1 oxygen. Now, what the problem actually asks is, what is the charge on copper? Right? You could figure that out either from the formula of the unit cell or from the ionic formula. But we know, because of where oxygen is in the periodic table, that its anion has a -2 charge. And we know an ionic formula has to end up with a neutral charge when we factor in the cations and the anions. So if 2 coppers have to add up to +2 to balance the charge of the oxide, then this is copper with a +1 charge. So this would be copper 1 oxide. The charge on the copper is +1 in that formula. And again, this kind of goes back to thinking about ionic compounds from chapter 2. So it's just sort of tying together these other sets of information that we have. Okay, that wraps up the practice test. So keep in mind, we'll be doing a review in lab as well. So there'll be lots more practice problems from the lab review. But don't forget about the textbook, particularly if there's a type of problem you are maybe not quite comfortable with. There's a nice set of problems that develop from simpler to more complex in that section of the textbook that would be another good resource as you're getting ready for the test.